What? Okay. Folks, you all should have the May-June 2023 paper. It should look like this item here. A trapezium drawn on a grid. Yeah? All right, cool. All right. Did Kayla go outside? Okay. All right, cool. Okay. All right, yeah. So let me jump back into it. Rohan going strong for us. Let me try a thing going. Okay, going again. So this is the May 2023 question. We have a trapezium labeled A, drawn on the grid there, the Cartesian plane. On the diagram above, draw the image of A after it undergoes. So the first thing they want is a what? They want a reflection in the line x equal to -1 and label this image A prime. Yeah. I thought it pointed up. It should be blue and oval. Oh, let me see what I can do. Speed. What are you trying to do? All right. Okay. So let me see what we're going. Right. And the next thing they want, right? The second thing they want here is a. So after it undergoes one and then translation with vector that. So the question is are these two things independent of each other or consecutive? Yeah. It wouldn't fit on the graph. Okay, good observation. Right. So we'll take each one of these independently of each other. What? One note. Yep. All right, cool. All right, guys. So our reflection line x equal to -1. So where would that line be? We talked about lines y equal to certain value. So if I had a line y equal to 4, right, that would be a perfectly horizontal line passing through 4 on the y-axis, right? The graph not straight, as you can see, right? If it was the line y equal to 2, it would be a perfectly horizontal line passing through 2 on the y-axis. Oh, look, Liam. Hey, Liam, good afternoon. How are you doing? Good to see you on. All right, cool. Right. Right. So we have y equal to those values. So if y equal to certain values is a horizontal line, when we have x equal to something, what kind of line would it be? Be a vertical line. So the line x equal to -1 would be a perfectly vertical line passing through what value? -1 on the x-axis. Because no matter how high or how low you go on that line, how far up or how far down, the x value is a constant. It's unchanging. All right. So the first thing they want is the reflection of the line into that. Sorry, the reflection of A in that line. So I'll give you a minute or two, see what you come up with. Right? Because we started a little before lunch. Yeah, we started about half past 10. Huh? Page. Watch my word, right? Watch my word, right? Imagine this trapezium was somebody's face, right? So that was the eyes and that was the smile, right? If that orange is a mirror line, basically asking to draw correct. Lumic. So Lumic, what they wanted to do is to reflect the shape into the orange line. All right. All right. Let me see. All right. Hey, YouTube, what vibes? Are they good? Nice. Right. Not here, man. That's the usual. Is there some kind of setting I could change? Do I just take off the mic? A translation is simply a shifting horizontally and or vertically. A reflection is if you're watching this thing here, you have an image there, right? So a translation will just shift something as it is. A reflection will cause it to flip like this. Right. So a vector has two components: a horizontal and a vertical. Yeah, the number on the top is the horizontal. If it's right, if the horizontal component is positive, you shift each point that many spaces to the right. Right, and then if the vertical component is negative, you go down. Yeah. Well, you had to hold on. You have to transit each vertex one at a time. Eh? So you'll do the top corner, and then you do the bottom corner. So translate. So you end up on the axis, right? Which year is this? This is May 2023. May 2023. Oh, my beautiful wife in chat. My beautiful wife, how are you? Are you still weak? How is the boy? Let him type something. How long is that now? Must be 5 minutes. Yeah, miss much. We had a session this morning. It did? All right, cool. All right, so let me see. So let me get a different video. All right. So first things first, let's get the reflection done. So the reflection of this shape in that line, you're gonna right here again. You're gonna use the vertices, right? The corners, as some people call them, of the shape, and you're going straight across or perpendicular to the mirror line. So from the bottom right hand side here, right? How many spaces we have to go to the mirror line? Two spaces. And then on the other side, when you reflect, you go the same number of spaces, right? So this point here will have its corresponding reflected point there, right? Now, you don't have to do that for all the other points. If you look at the shape, you can kind of figure out the rest, right? What I mean by that is think about it, right? This point here, you could count. You could say, okay, 1, 2, 3, 4, and then go 1, 2, 3, 4 on the other side. That's perfectly fine. You could do that. This point on the top here, right? 1, 2, 3, and 1, 2, 3. That point here. And then this last point here, you have 1, 2, 3, 4. So you go 1, 2, 3, 4 on the next side. And after it transit, after you reflect all the vertices, you then connect them. But any diagrams, yes, you draw in pencil. That's correct. You shouldn't. What time are we going up to? In this batch, 3 o'clock, and then we take a break for our one stop back at 4. Yeah. You shouldn't lose a mark. The reason I say pencil is because if you make a mistake and you can't erase, then you're kind of screwed. Yo. Yeah, no problems. Right. Time. Right. So, okay, now what we're doing is we're reflecting. If you think of a mirror and you're watching the mirror, so let's say there's a person's face, right? And there's a mirror here. So they want to see the reflection on the next side. The basic principles of reflection is that. Hold on, 1 second. From a very basic perspective, but not exactly. You have to follow certain protocols, right? This orange line is what we call the mirror line or the axis of reflection. So you're reflecting in that. So you have to have a mirror line in which you're reflecting, right? And the basic principle is, the basic part of it is that if you have a shape and you want to reflect it in a mirror line, you're going to take each of the corners, the vertices, right? So each of these corners, and you're going to reflect them. How we reflect is as follows. Basically, what you're going to do is you are going to go straight across to the mirror line. So from this point, we have how many spaces to go to get to the mirror line? 1, 2 spaces. When you reflect it, you have to use the same number of spaces on the next side. 1, 2. So the reflection of this point here will be at that point there. Are you okay with that? All right. Now let's go to this item on top of here. Let's use this vertex on top here, right? So to go to the mirror line, we have to move 3 spaces. So when we see the reflection now, it'll be the same number of spaces on the opposite side. So you'll go here. Cool. Right. Now let's go to the one top left-hand side, right? So we have to go 1, 2, 3, 4 spaces to the mirror line. So on the opposite side, we go the same 4 spaces to find where the reflection at that point would end up. And then the last one in the bottom here, it goes same 1, 2, 3, 4 spaces. You go 1, 2, 3, 4 spaces. All right? It'll be the same distance from the mirror line as the corresponding vertex in the original shape. All right, A prime. Humble, just for this session, when we start back, it's using some statistics and probability. It'll be very difficult to get a grade 1 if you do bad in paper 2. Yeah. Right, Q&A, is that any better? They told you that down here, right? It's a reflection in line x equal to -1. They have to. They can't just say reflect this. Say, okay, in what? So they have to give you the condition, the axis, right? Okay, and the next piece is, sorry, right? Translation with a vector for, okay, I did the wrong color, didn't I? All right. Let me just switch it. Whole thing. Right, so a translation is something just called a shift or a glide, right? So every translation must come with a vector. The vector has 2 components. The top one is the horizontal component, which means left or right, and the bottom one is the vertical component, which means up or down. Here, paper 2, sometime in June or July, probably June, not anytime soon. We have other things to worry about between now and then, like maths and multiple choice. Paper 2 done going. Right. So if your horizontal component is positive, you go into the right. If it's negative, you go into the left. The vertical component, if it's positive, you're going up. If it's negative, you're going down. So here, we go in 4 spaces to the right, and then 7 spaces down. So again, you start with the vertices. You take each corner and then move them. So let's start with this same bottom right-hand side one. So 1, 2, 3, 4. So it ends up by that same point, but we have to go down now. And we have to go down 7 spaces. 1, 2, 3, 4, 5, 6, 7. So here. Yeah. Like this. Okay. I should have asked why. Oh, okay. Thanks. SAR, you probably would. You probably would. But make sure nail only multiple choice for this. All right, let's do the bottom left-hand side now, right? So what is the vector? 4 and -7. So we have to go 1, 2, 3, 4 spaces there. and then down 7 spaces. So we're going to end up actually on the orange line. Okay, so that's this point here, right? Now we can do the rest if you want, or again, you could just try, you could draw any shape. We kind of know what the shape looks like, all right? But again, if you want to see these things in a little more detail, so let's do the top left-hand side, right? So 1, 2, 3, 4 to the right, and then 1, 2, 3, 4, 5, 6, 7 down. So we're there. And the last one, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7. And then you close up your sheet. And label it what? A double prime. Okay, cool. Yeah. So that, yeah, Nyla was correct. We couldn't each case here was independent, as in we couldn't do the reflection then the translation because these 2 points here would have come off the page of the grid. So yeah, so good job on that pickup, Nyla. All right. Will this be on your YouTube? Yes, it will. Yes, Jabari. Transformation's boring. Yeah, something's boring, something's not. You have to have the stamina and capacity to go through the boring. Okay, ladies and gents, have you any questions on what we did or how we did it? Right. Liam, talk to me. If you're good with that, let me know. Right. If you need me to re-explain anything, let me know that too. Right. So they tell us that we have a translation with vector 4 minus 7. Right? The vector of 4 minus 7 tells us how we're going to move this by shifting it horizontally and then vertically. All right? The top component here is the horizontal component, sorry. And the bottom component is the vertical component. So horizontal and then vertical, right? If it's a positive horizontal, you go into the right. If it was a negative horizontal, it will go to the left, right? Similarly with the vertical component, if it's positive, you go up. If it's negative, you go down. So here, are we going left or right? You asked me, and I started asking you. Yes. Try again. The translation vector is 4 minus 7. Might go on right. So 4 and minus 7. The top component here is the horizontal shift. The bottom component is the vertical shift. If the horizontal shift is positive, we go to the right. If it's negative, sorry, that's not right. We go to the right. If it's negative, we go to the left. So first question, the top component, is it positive or negative? So therefore, do we shift right or left? Right. The bottom component, if it's a positive, we go up. If it's a negative, we go down. So is this component negative or positive? So are we shifting up or down? All right, good. So now what we're going to do is we're going to go to the shape that we're trying to translate, right? And we take each vertex one at a time. Let's start with the bottom right-hand side. There's no rhyme or reason to start with any particular one once you do all 4 of them, right? So if we start with this, we have to shift right how many times? 4 times. And then down 7 times. Down here. So where you end up here, right? That's where this point or this vertex is going to end up. Huh? Okay. The next one, same thing. You're going to go 1, 2, 3, 4 to the right, and then 1, 2, 3, 4, 5, 6, 7 down. So we ended up there. The coordinates? Right. You could do that too, right? So guys, if anybody wants an alternative, what Juliana is saying is, if we took the coordinates, right, of any particular point, so like that point there has coordinates minus 3 on the x and 2 on the y, right? And if you add the transition vector, right? So minus 3 plus 4, and then 2 plus minus 7 is just 2 minus 7, right? Minus 3 plus 4 is 1, 2 minus 7 is minus 5. And if you look at where this vertex ended up, it did end up at 1 and minus 5. Right? So you could, yeah, that one is a little more efficient. Okay. And that's a double prime. All right. You need to teach math. Oh, yeah, I do. The answer somewhere else. They complete this card. You're kind. I do maths, advanced, and both if Chris should cut his hair.
No.
Oh, my wife asked it. Yeah. I told her I was gonna cut it last year for my birthday, and I cut off half of the length. And then it keep getting it's not getting as naughty as it was then. But then my 6 month old is now grabbing thing and pulling. So he busts up somebody here, so it's not as neat. So she like, maybe just cut it now. But me and Shiloh growing ours now. So he have his little boy bun. So I don't know. Maybe for my birthday. Maybe after the exam season done and then 43. So we'll do that. All right. Okay. Are we okay with this one? Any further question, anybody? We good? All right, cool. Well, then May 2024. All right. This is the next one page. So let me give you a list and I'll print the other. No disrespect. I just don't want to be like well, shit, you know, I'm thinking about it.
What's another fruit?
You gotta be local. That's a good question.
Calabash.
Calabash. Okay. All right, folks, you all have the question paper. Does anybody not have one? All right, that's now. So we did 2023. All right, so I'll put this to print. How many people? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now let's put these 10 to copy to print, and then we'll take a look, right? This is the next question anyway. Oh yeah, I like strawberries. All right, cool. There we go. Right, the diagram below shows a shape T and its image Q after a transformation. Okay, so let me get some colors going, right? So it shows the shape T, which I'll put in pink, and its image Q after the transformation. Okay, so let's zoom in that, right? Okay, so here the question. Describe fully the single transformation that maps the shape T onto shape Q. So look at shape T and look at shape Q. So what are the transformations available? We have translation, where you just shift it around, reflection, rotation, and enlargement. Okay. But yeah, it's probably reflection. Is it a rotation? If it was rotating, the diagonal wouldn't have flipped to the next way. Yeah. Enlargement, no, if it was an enlargement, it just would have gotten bigger. It could have got smaller, but it wouldn't have like shift around the orientation. It wouldn't look this. I mean, rotation is what some people might say, but you see what would happen is yeah, that diagonal line would always be on that side. No lie. Yeah, okay. Right. So yeah, it is a rotation. Sorry, a reflection. It is a reflection. Sorry, but you can't just say a reflection because what's this word here? Fully. Right? So a reflection is one thing. But when you have a reflection, you have to talk about the axis of reflection or the mirror line. All right? That is correct. right? Now, how do we find that axis of reflection? Hey, how are you doing, Marcus? I think I had just pull that one right up there. That's this page right here. Yeah, I had a spare. Yeah, give him that one. Right. Yo.
How did it see when you saw it? Doggy line.
I don't know. I don't know. I guess there was a specific pencil they wanted to use, right? Layer. They do, right? Layer. It looks like a rotation. It is an element of a tuning tip, but in this particular case, unfortunately, it's not a rotation. Sorry. Right? Okay. So how is it a reflection? Okay, let's take a look, right? So, all right, check this, right? How can I rotate it, boy?
Not right up on that.
All right. All right, check this. If it was a rotation, it would turn something like this, right? Or it could turn like this, yeah? Yeah. What I'm saying is that this what I'm doing here is rotation, right? Now hold on. Let's consider the original shape, right? The original shape is that pink one down there. So let's draw that over, right? So let's draw that. All right. And let me actually get a grid line going here. Let me change this to get a little too small. Let me do it as a big one. Yeah, that could work, right? Okay, let me get my dimensions here. So we have a 3 by 2 and a 1. Okay, cool. Right. Okay. So we have a 1, 2, 3 by a 2 by a 1 and then go so. Oh, nope, that's not what I wanted at all. We do some statistics and probability. Right? And the next one was I did agree for that one, right? Okay, cool. Let's take a look and see how that's shaped up. So, okay, cool. Where is Aru coming from, Red? I don't understand. Oh, right. Who? Yeah. Okay. Right. Okay, so check this, right? If we copy and paste that, right? If we were to rotate this, look at the diagonal, right? What we're trying to do is match up that diagonal, right? So with this diagonal here, I'm trying to see, okay, look, if it really is a rotation, can I rotate it somehow for it to match up exactly with what this is here? Right? Right? It's not matching up like that, right? Right? Yeah. So unfortunately, it's not a rotation. All right. Right. So what do we say? What do we say? A reflection in the X. Nah. It is a reflection. So now, if 36% of the Caribbean passed maths last year, will they bring an easier art exam? You had to ask them. I have no idea. All right. Right. Check this. What you could do, right? If you now, how can we tell without even considering right now where the axis is that it is a reflection? When we reflect something in a mirror line, right? Like you'll ever saw the TikTok where the lady put the towel up to the mirror and stick it and say, "How can you see me?" Because the mirror can't see me, right? So when she put her face here, the reflection is the opposite, right? So this side of her face mirroring on that side. So same thing here. This piece is mirroring here, right? Those two are close together, right? And then of course, well, what we could do to find the axis, if you're drawing the corresponding vertices, right? right? What was the protocol we used when we had the axis? We would count how many spaces from each point to the axis, and then go on the other side the same number of spaces, right? So let's take the longest blue. Actually, let's take this top line here. How many spaces in total here? 2, right? So that would be the total distance from one point to its reflection. So halfway between would be where the mirror line is, right? And half of 2 is equal to what? 1. All right. Same thing with this, the longest one here, right? You're going 1, 2, 3, 4. Half of 4 is what? 2. 1, 2. So it could pass here, right? So look at that. It could actually pass through right in between there. Right? So somebody in the chat had put y equal to x. That's correct. Yeah. Brady's the x, right? Right? So here, this is a reflection in the line y equal to x. How we know y equal to x? Because look at it. If you take any point along the line and you read down to the x and across to the y, don't we get the same value? Look here. Read down to the x across to the y. Same value, not so? Same thing here. You get 3 there, you get 3 there. You get 4 there, you get 4 there, etc., right? So the transformation that maps T onto Q is, a reflection in the line y equal to x, right? So that's the thing, right? On the diagram above, draw the shape, the image of shape T after it undergoes a what? A translation by which vector? That's what we just in the previous question. You shift in. Yeah, in the previous question we did here just now, it was 4 minus 7. That's the translation vector. So a translation is a shift, either horizontal, vertical, or both, right? Right? In the bracket they give you the what we call the components of the vector. Right? The top number is the horizontal component. It tells you how many spaces you go left or right. How do we know if you go left or right? We look at the sign. If it's positive, we go to the right. If it's negative, we go to the left. Is that positive or negative there? So which are we going? To the left. How many spaces? Once. Right? It was flipped, that's correct. What about the number below? That's the vertical component. It tells us how many spaces up or down we go. How do we know if you're going up or down? We look at the sign. If it's positive, we go up. If it's negative, we go down. Right. So you're shifting 1 space to the left and then 6 spaces up. And what I'll do, let me actually just paste this. Okay, no, that's not what to do. Sorry. Yeah. I'll just copy and paste this same page. But I'll take out all the extra lines on it, right? Cool. So we want to do a translation with vector minus 1, 6. Right? And again, if you feel like Jabari, that's correct. If you feel like you want to, you can always find the coordinates of each of the 4 vertices and just add that to the vector. True. You wish you write maths and POA last year? Maths wasn't so great last year for some people, huh? Bearings, sure, Shivam. Yeah, no problem. I think I have bearings in January. Check that one. Repeat. Right. So when you have a transition vector, right, that tells us that we're shifting the shape this many spaces horizontally and this many spaces vertically. A negative horizontal value means you're going to the left. If it was positive, you go to the right. A positive vertical value means you're going up. If it was a negative vertical value, it will go down. Right? So let's start with this point here. Right? We're shifting 1 space to the left and then 6 spaces up. So that will go here. What about this corner now? That vertex. 1 space to the left and then 1, 2, 3, 4, 5, 6 spaces up. All right. What about this one down here? 1 space to the left and then 1, 2, 3, 4, 5, 6 spaces up. And the bottom left-hand corner, again, 1 space to the left, and then 1, 2, 3, 4, 5, 6 spaces up. Here. All right, cool. Might be fried for C-sec max. Well, fried, cooked. Just make sure you season well so it tastes good. That's all. Right. Sorry, did I put A double prime? It's supposed to be M. My bad. I'm still working the last question in my head, yeah? So that's M. All right. All vectors and matrices are the E's in the syllabus. You find so? Okay, cool. Well, that's great. All right, Liam, talk to me. If you're okay with that, let me know. If you need me to go it over, let me know that too. All right, cool. All right, so that's in May 2024. Ladies and gents in class, have you any questions? Anything you want to re-explain? Any sore points, issues, problems? Good? All right, cool. All right, so I'll give a minute or so if anyone's copying some stuff down. Right, I think I put the Jan 2024 to print. Let me pull that one out and put the Jan 2023 to print. Do I want this one to print? We do only one pages now. Yeah, these topics always come back when you see it. This one, yeah, they bring some kind of transformation every year for sure. Transformation. Yeah, and YouTube. Who's it? Yeah, who can start some prompts from photo up as it. Yeah. Right. Continent, yeah. We do tricks already, sorry. Today we're doing this, statistics and probability. Tomorrow we're doing some patterns and sequences and some geometry. Oh, and some measurement, volume and that kind of thing. Okay. All right, guys, we did. Right. Does anyone not have a copy of the item on the screen? Right. The diagram below shows three triangles, P, Q, and R. Triangles Q and R are images of P after it undergoes a double transformation. Okay, thank you. Yeah, which means there was one transformation and a second one after that. So it means that it wasn't like in the previous two where you had one or the second one. This one happened and then the next one happened right after. So to the shape that was transformed, whatever was the transformed piece was then transformed again. Okay, so we have P to Q to R. P to Q to R. Describe fully the single transformation that maps triangle P onto triangle R. Okay, let's take a look. Look at some colors going now. Why not? Yeah, when it just shift it around. Yeah. Okay, yeah. So if you look at P and R, do they look reflected or rotated, or they look basically in the same orientation? Same orientation, right? Yeah. Well, if you put the translation vector, they'll know that it's a translation vector, but all you would have given is the vector. You wouldn't have said it's a translation. But the thing is, if you give a vector, where's it going to be? But no, they want the proper sentences. And there's 2 marks too, right? Translation, yeah, for sure. Right, so this is just a shift up or a translation, right? So yes, it's a translation because it's not a reflection, because if it was, then this side here would have been kind of facing us on this side here, and that's not the case, right? Right? It looks like it just took it and just moved it diagonally upwards. So that's a translation. All right. So the question is now, what is the vector? How many spaces horizontally and then vertically do we have to shift? Right. So what we do is we take a look at the corresponding vertices. So let's take the top ones, right? Remember, you either go horizontally, then vertically. So how many spaces horizontally would I have to shift that one to end up on it? 1, 2. And now vertically, do I go up or down? I go up. How many spaces? 2, 3, 4. Yeah. P onto R. But it's at the top. It's at the top here. Triangles Q and R are images of P after the goes translate. Right. So to go from P to R, we just shift it, right? It's a translation, right? So you could start by saying that it's a translation. But you can't just say it's a translation. You have to give the translation vector. What is a vector for a translation? It's how many spaces horizontally and then vertically you have to shift. How do we assess that? Well, we look at what we call corresponding vertices. So for example, if you look at the bottom, hold on, let's get a different color. If you look at the bottom right vertex down here, it corresponds to this one, not so? Right, so to get from that, the first orange point to the second one, horizontally, we'd have to shift 1, 2 spaces till we ended up directly underneath. And then we'd have to shift up 1, 2, 3, 4 spaces, right? So that would give us the translation vector, 2 horizontally and then 4 vertically. And remember, with translation vectors or vectors on the whole, the horizontal goes on top and the vertical goes below, right? Right? The horizontal goes on top, vertical goes below. And if it's positive, you go to the right. If it's negative, you go to the left. For the horizontal, for the vertical, if it's positive, you go up, and if it's negative, you go down. Right? So it's a translation with vector. Right? This is what we call the vector, the translation vector, or vector of translation. All right, cool. Yes, if it was a reflection, it'd be facing it. That's correct, yeah. All right, now they're asking about R onto Q. So let's put Q in a different color, shall we? So we want to go from the green to the purple. Now, if you look at the green and the purple, right? What are we thinking? It's not just a translation, because if it was a translation, right? It would have ended up looking like this, right? Does this look like this? No. It almost looks like if you rotate it, right? So if you were to rotate it, right, it does look like that, but it's not actually a rotation. We ask, well, why is that? Why is it not a rotation? Well, the corresponding lengths. Okay, so long story short, just like in the previous situation across, wait one here, right? It was a reflection, right? Look at it. The perfectly vertical face is facing the perfectly vertical face on that side, right? So that's why it was a reflection. Okay. So it's a reflection. So the next thing we have to analyze is where is the axis of reflection? So again, let's take the corresponding vertices, right? How many spaces between them? 1, 2, 3, 4. The axis of reflection will be exactly halfway between. What's half of 4? 2. Right? And that's passed through what point on the x-axis? 1. So the axis of reflection has an equation x equal to 1. So it's a reflection in line x equal to 1.
Oh, I get it.
Huh. Yeah, sure. How is it a reflection? Right? Right? So if for it to be a reflection, think about it, right? Imagine like it had a hat on here, right? And it had a face, right? And let's say it had the body down here, right? And it had, let's say it was like almost like a kind of Godzilla kind of thing, right? Cool. So if it's a reflection, what would happen is that this side here, right, would end up facing the mirror line, right? And or end up facing this side here, and it did. This line here corresponds to this side here, right? So if we do reflection, right? So the hat will be on top of here. Face would be here. Body. Then the so obviously it's not perfectly symmetrical. Anyhow, yeah. So long story short, right? It's a reflection. And then we could see that because of the orientation of the shapes. Right? The other shape, the purple one was laterally flipped relative to the green one. I feel like some items there. Well, I'll take a little walk and come back. I'll get some water. All right, but before we wrap up this, so again, it was just 4 marks, yeah, right? What was P to R? What was the trans? What type was it? Was the vector? And then from R to Q, what was it? I don't know that there is a single transformation that can map P onto Q. Again, it wouldn't be a rotation. Part of OA or POA? Because I do OA. And no, sorry, right now we're focusing on maths. Maths is Friday. POA gone. Next time is multiple choice after Friday, next week. Right. Okay, are we okay with that one, guys? That's it, Jan 2024. Anybody, any questions, anything?
Yes.
Good? Far side. Cheeks and Shamo. We good with that? Right. Am I doing any add maths, Yes. My assistant Misha is handling it though, so I personally might be doing it. All right, going again. All right, so let me print out this. Did I give you all Jan 22? Right, okay. Putting it to print. What am I gonna? Yeah, do you think? All right. Say Oaklandness. This is add maths now. This is regular maths. Add maths is after Friday. Yeah. Ignore the activity very top of the page. All right, guys. We'll leave it up on the board for a few. I'm gonna go upstairs to get some water and wash my face. Not power cut yet.
That's what I'm saying. I'll just get money back from my mom. No, you got it. Oh, you need 40?
Right, Fury. Not rubbish. That's the feel. I don't. I think they didn't think that's what they did, no? I feel like they feel like it was a nice exam. That's that PA we talked about. I agree. Okay. Okay, thanks. All right, guys. So diagram below shows triangle x, y, z. Well, x prime, y prime, and z prime, and x double prime, y double prime. Okay. Let me just get some colors so we could call them pink and the green. How about that? Object is the item that was then reflected or moved. So the object is the original item. Let's see what they're telling us here. Triangle x prime, y prime, z prime. That's the pink one, right? So triangle x prime, y prime, z prime is the image of triangle x, y, z. Now we have two triangles on the graph. The x prime, y prime, z prime, and the x double prime, y double prime, z double prime. We don't have the original, what's that? For real page yapping in the background. Page, you know Chocho? Iman says, tell Page ease me up. And Chocho77 says, for real page yapping in the background. No way. Well, they're calling you now. We are not doing it. I don't know. Tell Page ease me up. Tell Page ease me up. Page yapping for real.
Hi, I'm trying to learn. I don't know about all you, but I'm not yapping. I have no idea who that is.
Right. So we don't have the original item, XYZ, right? Now it says here, what does it say here? XYZ. So X prime, the pink one, is the original after an enlargement of scale factor 2 with center 5, 1. Okay. So what they're saying is that this item here is an enlargement of the original item called the object, right? And that enlargement has a scale factor of 2. So when you have a scale factor of 2, how many times? 2 times, correct. How many times bigger, right? Page, Talia or Talia says, ask Page how pure it was. Yeah, Page said it was good, Talia. All right. Now, it's an enlargement scale factor 2. So it's 2 times as large as the original object. So if this item is 2 times as large as the The original is what fraction of this one? Aha, very good. So we could actually get the size of the original triangle by looking at this one. But let's see. It also says with scale with center 5, 1. Now, what does that mean? With center 5, 1. So first of all, let's find 5, 1. Where's 5, 1 on the graph? 5 on the x is here, 1 on the y is here. So 5, 1 is your center of enlargement, right? So what we do with the center is we actually connect it to each of the vertices. Well, it's like 4 sessions tomorrow. It's like half a month. So like, can you say 300? Yeah. Oh, you're cool now?
Yes.
Right. Right. So we probably do a double on Saturday, double on Sunday. Whether confirm. Yeah. Okay. Yeah. Whether confirm for the days next week because next week I've got the exams. Yeah. So I'll just finish off. I'll probably like be around to help with like setting stuff on the question. Yeah. Yeah. And once she's here, and I'll go on that side and tell some admin work or play some game or something, you know. Right. So what we do is we draw a straight line from the center and connect it to each of the vertices. Right? Sorry, I was supposed to stop at the point, my bad. We have one more, right? That didn't work out too well. Okay. Right. All right. So check this, right? We have different ways we could go about finding the position of the original shape, right? One way is this. So just, I'm going to put back the lines, right? So check this. To get from the center to this point here, which is in the enlargement, right? Let's do like a vector. Let's get the horizontal and vertical. So we have to go 1, 2, 3, 4, 5, 6, 7, 8 to the left, and then 2 up, right? So we have to go 8 on the horizontal and 2 on the vertical. But this here is when it went to the enlarged shape. What was the scale factor of the enlargement? 2 times, which means that the enlarged shape is 2 times as far away from the center of enlargement as the original shape, right? So if these values here are double what the original shape is, what would the original values be? 4 and 1, right? So the original shape would simply be 4, 1, 2, 3, 4, and then 1 up. So the first point would be here. The Z point would be here, right? So let me explain that again. This is the center. This point here is the center of the enlargement, right? So to go from the center of enlargement to this point Z prime here, we went 8 spaces horizontally and 2 spaces vertically. But the principle behind the enlargement, one of the principles is that when you enlarge a shape, and it is an enlargement, right? Each of these vertices, right, is, in this case, because the scale factor is 2, each of these vertices is double the distance from the center, right? Double that distance relative to the original point. So if you reverse that statement, right? If you reverse it or invert it, the original point, therefore, is half the distance from the center to the enlarged point. Well, currently enlarged point, right? Now, what about to up here now? All right, so what would the horizontal shift be here? 1, 2, 3, 4, 5, 6. And in vertical, 1, 2, 3, 4, 5, 6. So in this case, to go from the center to the enlargement point for y, which is y prime here, you have to go 6 on the horizontal and then 6 on the vertical. So the original point would be halfway along those lines. What's half of 6? 3. So if you count 1, 2, 3, and then go up 1, 2, 3, We end up right here. Right? So that's the original point y. Right? And we could actually, we do even have to count for x, right? Because we know it's a right angle triangle, not so? So we could literally just draw it in right here. We could, or if y'all want to just see how it would be if we did for x the same way we did for y and z. The first thing is that I get a straight line going. Right, so to go from the center to the enlargement point, or to that point there, we have to go how many spaces? 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6 up. Right, so here it would just be 8 and 6. And again, that's when the scale factor is 2, so you went double the distance. So to go back to the original point, you have to find half now. Half of 8 is 4, half of 6 is 3. So 1, 2, 3, 4, and then 1, 2, 3. This point right here. So now, when you connect it up, that there is the original position and the original shape XYZ prior to any enlargement or reflection or rotation. Oh, sorry, you're correct. We should have used -6. But I was just, it didn't really matter per se because it wasn't actually a translation. But I understand what you say. Jaden, question 2, then try to kill me. Create an income statement, approve, and then balance sheet in the second halving. From one trial balance. Yeah, well, Jaden, those questions used to come regularly back in like the 90s and 2000s. So, go with it. All right. All right, so one more time, just in case anybody still not 100% sure. All right. So what they're saying in this first thing here is that XYZ, the pink triangle, is the image of triangle, the original triangle XYZ after an enlargement. Right? An enlargement does what to the shape? It can make it either bigger or smaller. And depending on if you have a minus sign, it could actually invert the shape too. It could change the orientation, right? Now, if the scale factor is a positive whole, well, positive first of all, we're going to get a bigger image than the original object, right? So the object is the original shape that was then enlarged. So the pink item is the enlargement of the original shape. So what they're asking us to find is the original shape. Now, in the yellow that I've highlighted there, they gave us the center of enlargement. The center of enlargement is the point from which the enlargement starts. So it's 5 on the x, 1 on the y. All right, so it's giving us this point here, 5, 1. Okay, so how do we go about finding where the original shape was? Right, so what we do is we connect that center point to one of the vertices. Sorry, that's not a straight line, my bad. Right. Now, there's a principle with enlargement that says when you enlarge a shape, the image, the enlarged item, will be this many times more away from the center of enlargement than the original shape. What's this number here? 2. So this shape is double the distance that the original shape is from the center of enlargement. So if this is double the distance and we want to find the original shape, we have to find half that distance. So what we could do is we could simply, oh, you going? All right, cool. Tomorrow is the day before maths. So you have maths. Yeah. Well, we have to have it. All right, cool. Later. Right, so to go from this point to that point, let's go horizontally first, right? Now, yes, we are going to the left, so you could do -6, it don't matter. Well, or not -6, this is actually this is actually 8 spaces going this way, right? And then 2 spaces going up. So we had 8 on the horizontal and then 2 on the vertical. So now, to go back to the original shape, you have to find half of those numbers. Why half? Because the scale factor is 2. So we doubled the size of the shape and we doubled the distance from the center of enlargement, both horizontally and vertically. So to go back to the original position, you have to undo doubling. To undo multiplication by 2, what do we do? Divide by 2 or multiply it by the inverse, which is a half, right? So a half of 8 will give us 4 and a half of 2 will give us 1. So we'll go from the center 4 spaces, and then 1 up. So here, that's where the original point Z would be. All right, let's talk about Y now. Right. So to go to Y, go to Y now, right? We have the same 1, 2, 3, 4, 5, 6 on the horizontal, and then 1, 2, 3, 4, 5, 6 up. Yep. Right. So the point Y, right? You had 6 on the horizontal and 6 also on the vertical. So the original Y point would be half of each of those. Half of 6 is 3, and then again half of 6 is 3. So from here you go 3 to the left, 3, and then 3 up. 1, 2, 3. So on that point. And then for the X point, right, okay, so for that last line now, so 1, 2, 3, 4, 5, 6, 7, 8 horizontally, and then 1, 2, 3, 4, 5, 6 up. So this last one had 8 on the horizontal and 6 on the vertical. So now, to find the location of the original point X, we'd find half of those. Yeah. Right, 1, 2, 3, 4, and then 1, 2, 3 up. Okay. So again, we'll just close it up real quick. Okay. So I hope that helps clear it up a little bit. If we draw in pencil, they will see when it's gone. Yeah, because you're supposed to use a number 2 pencil or something. So it should be very visible. Later we're doing some statistics and probability. This is a Y. Hello? All right, so that's that first piece there. So draw that on the grid above. Okay, what we're going to do actually is copy and paste so we could do the second piece but without the clutter of the first set of stuff. Take out that too. All right. The second piece says triangle X prime, Y prime, Z prime. So the pink is mapped onto the green by reflection in line P. State the equation in mirror line P. So they're saying that to go from pink to green, you reflect it. How do we find the mirror line? Statistics is 4 to 6 and half 6 to half 8. All right, so pick a point. Z. All right, so from this Z to that Z. So we go in how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And half of 10 is 5. So 1, 2, 3, 4, 5. So this line here, right? Oh, hey, yeah, organize that. Thank you. Right. And if you examine it, they say Y and Y. 1, 2, 3, 1, 2, 3. So both of those points, which correspond, were the same distance away from the mirror line, right? On opposite sides. Okay. So that line passes through what point on the x-axis? Wait, no construction, sorry. Well, you hope it come. Huh? The equation is x equal to 2. Very good. All right, Liam, let me know if you're good with this page, no? Please and thanks. Oh, I'd say if you're good with one on this page, let me know. The B or the, all right. All right, so one more time. So they're asking us here, they're telling us that the pink triangle is mapped onto the green triangle by reflection, right? In the line P. State the equation of the mirror line P. All right, cool. The mirror line must lie exactly halfway between the image and the object, right? So how we could do that is we could count the spaces between two corresponding points, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half of which is 5. So where they start from the left, from Z double prime, or the right, Z, right? They count 5, 3, 4, 5. This is where the line would be. Right? And that line passes through the value of what? 2 on the x-axis. So at every point on that line, no matter how high you go or how low you go, the value of x will always be equal to 2. Can I read in the comments? I did. Jules? Jules, I said 4 to 6 and a half, 6 to half, 8. All right, cool, no problem. All right, cool. That was the Jan 2022. Okay, so Jan 2021. All right, so I'll have print this for you guys. Jan 2021. We just did 2022, so 2021 is a what? That's 2021. That's not the question. I see in transformations 2022. Yeah, we just did that. All right. So this is it. Oh, it's 2 pages. Oops. Okay, cool. Right. So how to print out for you guys? Let's do that quickly. Ten. It joules. Diagram below shows 2 pentagons, P and Q, drawn on a grid made up of squares. Select the correct word from the list to complete the system below. Pentagon P is a what of Q? And give the reason for your choice in A part 1. So you all think? Reflection, rotation, enlargement, or translation? As a rotation, yeah? And give the reason for your choice. That's not wrong. I don't know if they'll consider it correct, but so it is a rotation. And yeah, the orientation is different. Right? We could clearly see it's a 90-degree anti-clockwise rotation. I'm not sure around what point. This one is Jan 2021. Huh? Congruent means that they're exactly the same. Yeah. Always. It don't really come, to be honest. Things that we learn from it will come, like similar and congruent. Like, for example, sine, cosine, and tangent. Those are trig ratios, but they come about because of similar triangles, right? F and Z angles are not, those are more parallel lines. But in similar triangles, if you have like parallel lines in the triangle, you create F and Z. But yeah, right. Right. We couldn't just put simple words. It was so congruent to it. Which year? The one we do now is Jan 2021. Right. In this particular one here, this would be congruent. Congruent means that they are exactly the same in terms of like the corresponding lengths and the area that the shapes cover. Not necessarily like orientation, but like for example, all right, cool. These 2 pages are the same exact page photocopy, right? If I turn this one this way, does it change the fact that they still show the same thing? And the size of this page and the size of the same thing? Right. So all that, they're still congruent. So that's what it means. It just means that they are exactly alike in terms of the lengths of the edges and hence the area of them. Right? And also in terms of that, what will also be the same as the angles on the inside, the corresponding angles. So none of the angles are the same, but I mean, that one it was all 90, right? So in this case, yeah, I would like to have said that this was rotated. So pentagon P is not opposite, it's not reflected, it's not trans, it's congruent. Yeah. Hold on, just now. Let me dig into that a little bit, right? So this length here would correspond to this length here. And if you notice, the length is like 5 blocks, right? So whether it was perfectly vertical or perfectly horizontal, right? This length here corresponds to this length down here. Those are both 3, right? This length here corresponds to this length here. Those are both 2, not so? Now the diagonal ones are a little more difficult to see, right? But let's try. Right, so this one here, sorry, no, my bad, right. Stop it, right. This one here, if you're drawing the rest of the triangle, you have like a 3x1 triangle, right? And if you look here, you have the same kind of 3x1 thing. So those 2 lengths are the same, right? And then the last side, right, so that's like a 2x2 right angle triangle, and the same thing here. Those 2 sides correspond, right? 2x2. Right? So because we could see that all of the corresponding lengths or side edges are the same length, the shapes are congruent. And by extension, the corresponding internal angles between the 2 shapes are also equal. They are congruent. Right? So give a reason as 1 mark. The corresponding lengths between the shapes are the same length. If it was just shifted left, right, up, or down. Right? In this case, the orientations are clearly different. Matrices and vectors as tested as editor already. Sorry. I'll see if I can fit it in, but it wouldn't be today. Miru. Oh, wait on. With the Miru. Yeah. Please, thanks. Yeah. Usual thing is. Right. Sorry. Which one is rotation in the box of option? Oh, sorry, none. Biggest topics of studies for? Well, every question in the paper is about the same number of marks, right? Or close enough. Hold on. The section 2 section is what? 12 marks each. Because if you have 7 by 9, that's 63, and then 12 by 3 is 96. Yeah, so the section 2 questions are more. Tessie, I have a matrices playlist. The vectors, I'm not sure I have that one. But you'll find matrices there for sure. All right. So that's the first half of the 2021 Jan, right? We'll do the second piece. I'll print out 2020 for you, but I'm gonna have to leave to go and collect my son. I wanna come back down in time. Yeah, it's already almost 10 to 3. Wow. Okay, cool. Next page now. All right, so here now, the letter A and point C, which is 6, 6, are shown in the grid below. All right. On the diagram, draw accurately the letter A, the enlargement of A by scale factor 2, and then the translation of A using the vector minus 3 and 2. Okay, interesting. Okay. What time am I coming back? Oh. So about an hour. So, huh? I gotta go for my son, pick up my mother-in-law and the babysitter, drop them and then come back here. On up by the traffic light, sure. Put the car in neutral and put up the handbrakes. Hey, you trick that one, right? I've done that a couple times before when I felt like I needed it, right? But then you see the problem is in the night. Now, a couple times it didn't matter. I knock out my head hit the pillow to put my son to sleep, I knock out. Right? My wife finish, she bottles everything, come back, she like he was tired yesterday, like, huh? Yeah. Anyhow, a couple other times, I said, okay, I'll handle the bottles tonight, don't worry about it. Washing bottles, washing wares, pack away the wares, clean the table, fold some clothes. 10 minutes. 2 o'clock. Shit. But then when I go to bed too, I have a hard get up at 5:30. Eh? I could push it to 6, but then we're leaving late. Right? So yeah, I surviving on prayers and caffeine right now. From Starbucks? Once. I don't know. It just tastes so bad. I was like, never again. Never again. I just like the hot. The hot have a comforted. I like cold drinks, but it just I guess I wasn't accustomed. So I do as give things a fair chance, give a chance of twice. Mark 3, if by the third time, it I take mine done. I might give it a few years. So the cold brew I tried once, I was like, I don't put sugar or cream. I just take black coffee. Or dope you. I do that. But I think paper 1 and S1 give you a 3. Not by itself. Don't know much for maths. Something. Okay. Not sure what that song like. Anyway. All right. So check this. When we say good, everybody need espresso. I'm going to get IV and just plug it in. Well, you want to see my class right now? A pot. Head down, head down, head down. Well, she up. Okay, cool. Pressure. Yeah, now it's that time for the afternoon crash. Anyhow, wait, what YouTube saying there? All right. Yeah, had some parts I liked, some parts I didn't like. Yeah, we're going on. All right. Okay. All right, guys. Let me do these two. Check this, right? Even if the enlargement given trouble, the translation should be okay. What happens in a translation? It is shifting it horizontally, vertically, right? So if we shift it horizontally, right? The minus 3, 2. Minus 3 is the which component? Horizontal or vertical? All right, just now, hold on. I'm trying to find my bearings here. What? That's not what I wanted to do. Leave yourself. On to the next page. Right. Right. Okay. So minus 3. The -3 here is the horizontal. But if I'm shifting -3, which way am I going? Left or right? Left. How many spaces? 3. 1, 2, 3. And then the next number is the vertical component. That's 2. But it's a positive. Do I go up or down? Up. So I'm going up 2 spaces. 1, 2. So I'm going to be here. All right. The next one. So -3. 1, 2, 3. Up 2. 1, 2. So I'm going here. This is the easier one first. Yeah, cool. So this one. 1, 2, 3, up 2. You could, if you fit one and you see how the shape organized, you could draw it in. Once you have 1 point and you can see how the shape, in this is the letter is drawn, just draw in the rest. What happening? A what? No? No? In the middle of the day? This is like a good luck for exams or something? Okay. Well, as they say, strike while the iron hot, eh? Well, that's because you're pay for the tattoo. All right, so that's the 3 minus 2. And let me do the good. Let me do the enlargement real quick. Now, okay, so sorry, the question I was asking about was with an enlargement, right? The shape could either get big or get small. Yeah. Or just take that alone. Yeah, that's it there. Yeah, whole and blank. Right. So with an enlargement, 2021, John. With an enlargement, you get bigger if the scale factor is a positive number, positive integer being a whole number. If it's a fraction, obviously it's going to get smaller, right? Okay. Now, the good thing about the scale factor 2 tells us what? How many times bigger each side is going to be than the original shape. All right? But it also has a center of enlargement, right? That gives us a reference point, right? Because basically the enlargement is like, all right, you all know like shadow puppets, right? Like if you put a torch out and you put your hand, right? And the further you put your hand from the light, the smaller the shadow is. And when you bring your hand closer to it, right? It gets bigger. Right. So it's a similar concept here. Similar. So you have to have a center of enlargement. That's basically where you're shining torchlight from, right? And again, if the torchlight is very strong and you put the torchlight and you put the thing here, right? The further the shadow go, is the bigger. Sorry, the further the light goes, the bigger the shadow will be, right? Okay, cool. Like if you go right up to the wall, it goes small. As you start to walk back, what happens to the shadow? It gets bigger, right? So that's what the scale factor does. The bigger the scale factor is, the further you're shining light. So the bigger the item will seem. And the further away from the torchlight it will be, right? Now, check this. From the center of enlargement to the top here, if we analyze the horizontal and the vertical, we have 1, 2 horizontal to the left and then 2 down, right? The corresponding point to this here in the enlarged shape will be double the distance as that point. So to get from the center to that original top point, you go 2 left, 2 down. So if your scale factor is 2, then you have to go double the horizontal and double the vertical to get to the enlarged point, right? So if each of those is 2 and you multiply the scale factor by them, 2 by 2 is what? 4, right? So we have to go 1, 2, 3, 4, and then go 1, 2, 3, 4 down. Now from here, you could draw in the rest of your shape. Just remember to draw it twice as big. Or if you want to play it safe, let's check the rest. Okay? Right, so that's the first point. So this point and this point correspond, right? Different color now. Okay, let's go to the bottom right-hand side. Okay, so horizontally, we went 1 space to the left, and then vertically, we went 1, 2, 3, 4 spaces down, right? So if you double each of those, so 1 left, if you double 1, you get 2. If you double 4, you get 8. So instead of going 1 and 4, you go 1, 2, And then 1, 2, 3, 4, 5, 6, 7, 8 down. So that corresponds to the blue down there. Right? And we have one more point to go, which is the what? The bottom left-hand side. This point here. All right, so there we go. So to get from that point, from the center to that point, we have to go 1, 2, 3 to the left, and then 1, 2, 3, 4 down, not so? So now to get to the corresponding point, when you do the enlargement, you have to go double. Double 3 is 6, and double 4 is 8. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, 8. So down here. Sorry, I cut the last one kind of short. Right? So we have the 3 points there. So now let's connect them up. You're going to go here to here, here to here, and then this will actually be on the axis itself. Yo. Enlargement?
Yeah.
Uh-huh. Actually, as in, if you're supposed to connect them, well, the points, both points should lie on the same rate, the same line. Yeah. So check it. If that is correct, right? So if we draw a line through here and here, we're checking those 2 points, right? And if we draw it between these two, should also connect them, right? And then the last 2. Oh, you see it now? Right. All right. Okay. Jesse, I'm real sorry. I have to cut right now and go and pick up my son because I had a start back class at 4 o'clock. That's some traffic, right? So this replay is already live on YouTube, so you could always just go to like the last 15 minutes and check it out. Okay, but this is the Jan 2021. All right, guys, we're breaking for an hour now. I might probably be late, I ain't gonna lie. But when we start back, we're gonna hit some stats and probability, right? This? Yeah. Uh-huh. That might be from like 2021 or 20. I can't tell you when last I do this, to be honest. I have replays. I don't have like produce. The only one I have is matrices. I have a matrix playlist, but I never did more after that. Yeah, that's from 2019. That's the year I started. But I started with accounts, and I was like, well, people can have only the accounts and cover the maths, so they must be into accounts. The TikTok name when it's maths. Name the same name? Adaptation. Yeah, guys. So YouTube, I cut it out there for a little bit. See you all here. Liam, I'm going.